Good morning, everyone. My name is Diana Borrego, and I'm a researcher at the University of Seville. On behalf of my colleagues, I'd like to thank you for watching the presentation of our paper called Problem Generalization for Designing Recursive Algorithms. First, I'm going to briefly introduce some concepts and present the methodology. Then, I'll detail the concrete process proposed in our contribution, illustrating it with an example. Finally, I'll enumerate some conclusions. Let's start with the introduction. Computer science university students have the need to develop computational thinking, which is the mental process used to formulate problems whose solutions can be carried out by the computer. Computational thinking includes skills such as modeling and breaking down problems, processing data, creating algorithms, and generalizing them. Therefore, students must acquire computational thinking to be able to carry out problem solving through modularization, top-down analysis, bottom-up analysis, and also, for example, recursion. Particularly, the understanding and application of this last concept of recursion requires the students to make an extra mental effort. They usually understand and learn more easily the iterative formulation of problems. However, to understand the recursive formulation, a special type of thinking is needed, and therefore to be able to use recursive thinking. This presents a difficulty that makes a mental predisposition necessary that is not always frequent or easy to reach depending on each person. In detail, the recursive resolution of a problem is raised when the specification of its solution is made based on the solution of other problems of the same nature but smaller size. A recursive algorithm is one that expresses the solution of a problem in terms of invoking itself. Therefore, every recursive definition has base cases, encompassing and resolving cases where the resolution of the problem is direct and does not require the use of the function being defined, recursive cases, which are those whose resolution does require the use of the function being defined, and the size of the problem, which is a cardinal indicating the dimension of the problem to be solved and that decreases in each subproblem. Not all recursive definitions are suitable for building an algorithm. To be adequate, they must have at least one base case, and in each recursive step, the size should be reduced, which implies that the execution of the algorithm will end. Let's now present the proposed methodology to facilitate the modeling and resolution of recursive problems. Since taking into account the aforementioned and to facilitate the acquisition and application of recursive thinking, this paper proposes to carry out two steps prior to the design of a recursive algorithm to solve a given problem as shown in the figure. Specifically, these steps are: 1. The generalization of the problem through a set of problems. More precisely, generalizing consists of adding properties to the original problem to consider it a particular case of a wider set of problems. And 2. The specification of the solution to the problem through a predefined specification sheet based on the previous generalization made. This sheet contains different fields that correspond to the characteristics that are relevant to solve this problem recursively. In detail, regarding the problem generalization, in a recursive definition, it is always necessary to start from a set of problems. In such set, each problem is characterized by a set of properties. Each property of a set of problems can be categorized as share, which are defined as properties of the set of problems that take the same value for all problems of such set, and individual, which are defined as properties of a set of problems that take different values for each problem of such set. Moreover, each problem has a specific size, that is a derived individual property. The size is defined as an integer that is related to the complexity of the problem, that is, how far is the problem from a base case. There are different ways of defining the size of a problem, being necessary to check the correctness of such definition by considering that it should be a function over some of the properties of the problem and be reduced as a base case is approached. Within a set of problems, each problem can be categorized as base case when it has a direct solution without need to perform a recursive call. A problem that is a base case has a small size. Moreover, there can exist several base cases within the same set of problems. And recursive case, when it does not have a direct solution, that is, it is necessary to perform a recursive call to solve it. The solution of a recursive problem is defined by combining the solutions related to problems of smaller sizes, that is, subproblems. All problems in the set of problems of interest verify a predicate D. This predicate establishes the domain of valid problems. The key idea to solve a problem in a recursive way is based on expressing its solution in terms of operations over solutions to a set of problems of a smaller size. For this, in many cases, it becomes necessary to imagine that set of problems from the original problem, that is, the problem generalization. To be more precise, the problem generalization consists of the following steps. Adding, if necessary, a set of additional properties to those that already had the problem and classify them into classic, derived, individual, shared, and so on. Defining the domain of problems of interest through a predicate. Defining the size of a problem. Stating the base cases and the recursive cases. Specifying how each recursive case is reduced to subproblems with a smaller size. Specifying how each recursive case solution is related to that of its subproblems. Specifying the solution of base cases. And finally, indicate which of the problems in the problem set corresponds to the original problem. Regarding the specification sheet for the problem generalization, this slide shows the general structure of a recursive algorithm on the left, and its corresponding with the specification sheet appears on the right. The sheet collects all the information about the recursive problem to solve, such as, for example, the functions that return the size of a problem or the solution of a base case. The use of the specification sheet helps to systematize the resolution of recursive problems, thus facilitating its approach by the students. The proposed approach is applied to some illustrative examples, such as the Fibonacci numbers. The Fibonacci numbers can be recursively defined as shown. Regarding such definition, a recursive algorithm can be designed according to the specification sheet related to the problem generalization. Finally, main conclusions are listed. Analyzing the solution to a problem before carrying out the implementation itself facilitates error isolation as well as error detection. Generalization of problems and the related specification sheet allow for establishing a systematic way of designing a recursive algorithm for solving a specific problem. Through this step-by-step methodology, students can understand and learn recursive reasoning more quickly and easily. Thank you so much for watching this presentation. If you have any questions or comments, please don't hesitate to contact us by email.